Hello all, in this video we will learn about different fine-tuning techniques. We will focus on parameter efficient fine-tuning methods, that is PEFT. A little more focus would be on LoRa, that is low rank adaptation method. So I would suggest you to look at the part 1 video for a better understanding of this video. In this video, we will learn about what happens to the LLMs during the fine-tuning phase. And we will learn about the types of parameter efficient techniques. A little more focus we will have on LoRa. We will understand how it makes the large language model better during the fine-tuning phase. Finally, we will understand through a Google Colab by using a Python code. We will implement a PEFT on Google Flantify model for summarization task. Okay, so before understanding the types of fine-tuning, we need to understand what happens to large language model during the fine-tuning phase. Thanks to dailydose-of-datascience.com for the reference material. Let's say we are expecting the large language model to do a QA task, that is question answering task. And the domain that we are focusing is a medical domain. So let's assume this. So we have, when we have a use case in front of us, the understanding would get better. So that's the point. So I'm trying to make it here. Okay, so this is the architecture of the large language model. We have the multi-head attention layers and the feed-forward layers. We'll have a number of layers like this. And to fine-tune for this task, we need to supply so many prompts and the responses as a data set. Okay, so we will give the prompt and we expect the model to extract the details of the patient from the prescription. So here that is the task. So extract the patient details from the prescription. It extracts. To do this, we would have supplied so many prompts and responses. Okay, so we will just have a closer view inside, like what happens to the large language model during this process. This color-coded layers represent the base architecture of the model. So that is the original large language model layer. So this would already range from million parameter size to a billion parameter size. Okay, so now these color-coded layers represent the added layers. So the added knowledge that we are supplying for the fine-tuning task. Okay, so during this fine tuning, we would need to change the weights of the model because we are changing the knowledge adapted by the large language model. So we need to tweak the weights or the parameters of the model so that the additional knowledge is actually accommodated by the model. So this is what is the core idea. Okay, so we will have more number of forward passes and the backward passes during this process. So during the forward passes, we will inject the data set and see how the model is behaving. Is it able to do the extraction properly? So that is the information extraction properly. During the backward passes, if we are not satisfied by the model performance, we would need to tweak the model weights. That's what happens during the backward pass. So the gradient represents how much change we are making in weights for each and every parameter of the model. So this is the overall idea. So we will have n number of forward passes and backward passes during the fine tuning. Okay, so this is the idea. So we will just see the types of fine tuning. So the full fine tuning. So what we saw now is actually full fine tuning. So what happens during full fine tuning is that during the backward pass, we will expect to change all the weights of the model. So including the base model weight. So that's going to throw a lot of burden to the computational resource. Why? Because it's already million or billion parameter size. So then for each and every backward pass, we are changing all the weights of the model. So this is only possible with large enterprises, but fine tuning is done by most of the researchers or the smaller enterprises. So if this is going to be the case, then we might need more number of GPUs. So, and if that is not practically possible, so then these LLMs would not be much use to us. But that's what is expected out of full fine tuning. So for 6.7 billion parameter model for a Llama 7B, so we might need 320 GB GPU, so which is not practical for most of the researchers or the smaller enterprises. So, but that's how it is. So to avoid this, researchers came up with the PEFT technique. So that is what we are going to see now. Okay, so the first technique that was proposed was by Google researchers, that is adapter based fine tuning. So, what they suggested is that, okay, so this is the transformer block that we already have. We will change this architecture by adding adapters in each and every layer. So, in each and every layer, we will have the adapter. This adapter will have the extra weights. So, what we mean is that during we will look at this picture. So, this weights will be frozen. The base model weight will be frozen. Only the adapter will be changing the added layer weights. So that's what it means. So we will, that's what Google researchers came up with this. So we will have adapters in each and every, how many ever connected layers are there, we will inject the adapters. So that's what they came up with. So this would actually reduce the percentage of parameters, trainable parameters. So we are not in full fine tuning. So we are expecting the 100% of parameters to change. We are not expecting that. So we were only updating the parameters, changing the parameters by 1 to 2%. So we might need only 80 GB GPU. So that's better than the 320 GB GPU that we saw earlier. So that's what adapter based fine tuning method um, means. And low rank adaptation, so better than adapters. So this was proposed by Microsoft researchers. So I will put all the links of the base papers in the description so you can have a look at it. So what low rank adaptation does to the model is that it does not change the architecture of the model like what adapters does. So what happens in the adapters is that it is changing the architecture of the model, right? So but what happens when we change the architecture of the model? So you will see an adapter here, right? So you will have more adapters like this. So during the backward pass, it is not going to throw any problem because the base model weights are already frozen. Only we are only changing the weights of the adapters. That's fine. But during the forward pass, when we inject the input and when we expect the output, these adapters get active and there will be delay in the inferencing time. So that is the computational burden that it is adding. So to overcome this, Microsoft researchers came up with the idea of low rank adaptation. So we are not going to change the architecture of the model, so but we will only take a low rank matrix, the sub matrix of the original matrix, and we will fine tune those, and we will put the add the matrices. We will understand this better in the upcoming slides. You don't need to worry. I'm just giving you a very overview of what is LoRa. So to as of now, we can understand that we will only take a sub part of the matrices, fine tune it, and add it to the original matrix. So these weights or parameters are in the form of matrix. So that's why I'm talking about matrix here. So we are not changing. So the difference between adapters and low rank adaptation we can think of is that so LoRa introduces low rank matrices inside the attention layer, which is smaller than the full adapter modules. That's the point I'm trying to make. We will understand little more about the math in the upcoming slide. So, but that was proposed by Microsoft researchers. So, during the inference time, we are not disturbing the model. So, what QLoRa does is that it was proposed by Meta AI researchers. It is better than even LoRa, but what LoRa does is that it only injects low rank matrices to reduce the burden of the computational power. But what QLoRa does is that it reduces the bit. So it quantizes the bit. So from 16 bit, if you're having a 16 bit value for the weights, it so basically when we reduces the bit, what happens is that like we are reducing the rounding of the values of each and every weight values. So when we do that, so even more the spaces are the spaces are compact, and we can run it on a even lesser GPU. So that's what they propose in QLoRa. Okay. So another fine tuning method that was proposed by Google researchers is that like prompt tuning or prefix tuning. I think we saw this in the last video. So this is very cheapest. Like we are not we are not updating any parameters technically, but we'll just instruct the large language models with a prompt. So summarize the following and we will give the prompt. So it will be able to do. So prefix is like just add a prefix to it, like add creator, tell a fantasy story about a dragon. So this is called as prefix. So for this, the model should already, so remember, so to use this technique, like as we saw in the earlier video, so for this, the model should have already the domain knowledge. So if it is able to do so, like we can go for prompt tuning or a prefix tuning. So all these technique, adapter-based LoRa, QLoRa, and prompt tuning comes under the category of PEFT. So, but we will understand a little more of LoRa, what happens during LoRa fine tuning. So we'll get the math done. So we said like, yeah, so this is the original layer. So this is going to be frozen as an adapter, and we are only going to change the added layers. But how are we going to do when compared to the adapter model? So this W is the original weight matrix. So it is having D by D dimensions. It can be 3 by 3 or it's not technically 3 by 3. So it is based on the number of parameters um, it is trained with. Okay, so now what we are going to do is that with this matrix, we are only going to take two low rank matrix A and B, and we are going to reduce the dimension of the matrix, and we are going to change the weights, and we are going to finally add with the original matrix, and that's how we are going to do. So it's okay if you're not able to understand at this point, so you'll definitely understand here. So the pre-trained weights, let's say the pre-trained weights is this W1, W1, 2. So for easy understanding, I've taken 3 by 3. So the fine-tuned weights is nothing but like the changed weights. So these are going to be the changed weights. The pre-trained weights will be frozen. So that we know. But the fine-tuned weights, we are going to make the little change in this. But we are not going to take the entire matrix of 3 by 3. We will only take a few of these weights and we will do it. So we'll split this matrix into A matrix and B matrix, and we will do the math. So we will understand how this is done. All right. So this is the pre-trained weight. So that is W. So we will denote as this W matrix. So this is frozen. And okay. So fine-tuned weight, we are going to make the change. That is 3 by 3. That is delta W. The final model will have this delta W plus this input plus bias. This is how the final model will look like. But how this delta W is worked out, so we will see. So let's say this is a delta W, so that is representing this number. So this is 3 by 3. Originally, if you look at in the real time, so this 3 by 3 is not 3 by 3 actually. So it is going to be billion by billion or million by million. So, but if we are able to, if we are, even if it is only, we are only changing the weights of this fine-tuned weights and we are keeping the original weights frozen, it's still a burden, right? Like, so what LoRa does to this is that to this weight, the additional delta W, so it identifies linearly independent columns and it takes it out. That's what this rank mechanism says. We will understand how we fix this rank to be 1 here. We will understand. So let's focus on this column 1, 2, 3. So it is linearly independent, right? Like, because this is the first column, so it is not dependent on any other column. But when we look at the second column, it is dependent, it is easily dependent on the first column, because when you multiply the first column with 2, so you get the second column. That's same case with third column. So when we multiply the first column with 3, so we get the third column. So the idea is that when we talk about LLMs, what these are going to be the weights. So that means we can get this information through when we only process the first column. So we take out the first column and we do the changes and we can easily compute it later. So that's what is the idea. So during the fine tuning phase, we take out the linearly independent columns. That's why the rank is 1. If we have two linearly independent columns, the rank would have been 2. So that's the idea. That's the math behind. Okay, so now we are splitting this matrix into 3 by 1 matrix, that is A, and B is the 1 by 3 matrix. So we are only working on these two matrices. That's what this picture would have represented. So we are not working on the entire fine-tuned weights. So we are further breaking it down to a smaller A and B matrix. Okay. So this, how did we get this 1, 2, 3? So this 1, 2, 3 represents the coefficients of this matrix. So when we multiply by 2, we get the second column, and when we multiply by 3, we get the third column. That's what this B matrix represents. That's the math behind it. Okay, so when we multiply together, we get the delta B. So we are only taking the linearly independent columns, and we are changing the weights. So during the fine tune process, like just imagine, so we are reducing the dimensions to a larger extent when we do so, because like instead of 3 by 3, we are only working on 3 by 1 and 1 by 3 matrices. That will reduce the burden to a larger extent than we think. So then what LoRa does is that, like after doing this delta, it will add to the original weight matrix. So primarily, it is not changing the architecture of the model like what adapter did. So adapter change added the extra layer to the model, but here this LoRa mechanism is only adding directly the additional weights. So this is not going to, delay the process during the fast inference. So that's how LoRa is better than the adapter module. So and finally, you can have, these are the hyperparameters that we need to tune during LoRa. This is a scaling factor, and to have the values tractable, and this is R is the rank. So this is the math behind this. Like just to have a summary, like what LoRa does is that, like it freezes the pre-trained weights, but even for the fine tune to change the during the backward pass, to change the fine tuned weights, it is not taking the actual metrics. It is taking the two low rank matrices, and it is trying to inject during the in the attention layer. So that's why the name is low rank adaptation. So that's how it is actually pulling down the computational resources needed. Okay, so this is what we get when we inject LoRa. So if the rank is 1 for a 7 billion parameter, the actual parameters trained are only 167 k parameters. So if the rank is 2, it is 34 k parameters. Even if for the worst case, if the rank is high, 8192, so it's only 1.4 b. So look at the reduction from 7b. We are not training all the 7b parameters, we are only training the 1.4b parameters. So that's actually good for the computational resources. So when we look at in terms of percentages, so it's almost negligible, right? Like when we have rank 1, so we won't practically have rank 1, because just because like we saw 3 by 3 matrices, we were able to pull out one linearly independent matrix, but in the real time, it's going to be a billion, a billion dimensions. So then it's the rank would be normally high. So for rank 1, it is 0, it is negligible. So you see the percentage of reduction in the trainable parameters. So that's what I wanted to convey here. Okay, so that's what I had to say about how LoRa reduces the dimension and reduces the GPU power while during fine tuning. So we will look at a code. So this is the code I got from um, yeah, so I got from Hugging Face. So thanks to this contributor, so KN Karthik. So this data set I grabbed it from Hugging Face. So the model we are going to use is the Google FLAN-T5 model. Let me locate it. So this is about the data sets. So we will install the data sets. So this is about the root score. So root score is used to evaluate the outcome. So since we are focusing on a summarization task here, so for summarization task, we use root score to calculate how good is the summary. Yeah. So we have installed all the preliminary libraries. So I've already run this code to save time. So I will put this code link in the description. So if you want to edit this code, So as I always say, you can save a copy in Drive and you can edit it. Yeah. So this is the data set, and yeah, so here is the model. So it will create a copy for you. To in that, like, you can edit. So I've only given the view permission. So this is by the Google Flantify base model. So this is already a million parameter model that we are using. Okay, so we will see like how PEFT works on this. So we won't see the inherent map that we saw just now. So yeah, so we will, so the data set is loaded and we've loaded the base model. And as we saw in the fine tuning video part one, this is the format data set, the base model, and we'll need to go for the parameters. So we'll straightly go to the parameters. So if we look at the parameters, R is a rank. So we have fixed the rank to be 32 here. And this is a scaling factor, so that we saw in the slides. So the scaling factor keeps the model stable, and it keeps the values tractable. So these are the the targeted modules where the weights are actually changed. The dropouts are for regularization. And yes, we are keeping the bias to be none. And this is a seek to seek model. So Flantify is a seek to seek model. So these are the configuration we need to configure during the fine tuning phase. Okay, so this small piece of code will actually inject PEFT. So we are loading the original model, that is Flantify, and the LoRa configuration parameters that we saw. So the trainable model parameters is this much. So that is so the total parameters of the model is actually million parameter model. So I think it is 1.4 million. I'm not sure on that. Okay, so yeah, so the trainable parameter we have reduced to this size. Yeah, so we will get the output. So these are the training codes. So I'm not focusing on that. We will straight away go to the output. So here we will see the original model. So original model, the root score is zero point 0.2. So but you can see that like even when we have done it with more efficiency, so the root score is 0.26. It has actually gotten better. So with the PEFT model, we are able to achieve even a better root score. So what is root score? So a little more details about the data set. So data set contains around 14,000 summaries. So the original summaries and the PEFT summaries. So it will also have a reference summary. The root score is calculating how good is the summary when compared to the human generated summary that is in the data set. So that's what it primarily calculate the overlap of the n-grams. The n-grams are nothing but the words. So that's how the root score work. Yeah. So what I wanted to convey here is that using PEFT, so keeping the rank to be 32 for a million parameter model like Google Flantify, so we were able to reduce the number of parameters to a larger extent and still achieve a good root score using PEFT model. So that's what I had to say about a PEFT fine tuning using LoRa for a summarization task. Hope you understood the technique about fine tuning. Thank you.